Okay, now officially good morning and let us start the lesson. So I think this would be the last session that I want to have this detour. Might be in the future we also come back again to this topic. But after that we go back to vectors. That will start next session. But let me just finalize what we have started so far. So do you remember we introduced a theorem which was famous, and that was Sevas theorem. And this means that this tells you that if I have any triangle, yes, any triangle ABC, if I have three concurrent Sevian lines, okay, this is not a necessity that the Sevian lines are concurrent, but if in case I have concurrent Sevian lines, for example, one of them, let us call it Bx, and then let me call the other one By, Ax, and then, for example, this one, might be a good idea to use the ruler, and the other one, so because there is no guarantee that random Sevian lines passes through the same point, but assume that the third one also passes through this, and I call it CZ. And then we had a very famous relation that's happening, and do you remember what was that? You need to improve your memory, really. This is a have to. So what should I write? Do you remember?
AZ over CB.
AZ over ZB.
Times BX over XC.
Bx over xc
Times Z is CY over YA
over ya
is equal to what?
is equal to. Yes. So that was the Sevas theorem. And I enjoyed the proof when I read it. It was very nice. So it related to the areas of the triangles involved in this picture, and then using that we were able to show that this is the case. Today I want to show the converse of the Sevas theorem, and then you will see that we can unite all of those concurrency problems into one setup. Okay? So what do I mean? So I mean that if someone tells me that I have three Sevian lines and I checked this condition holds, I want to conclude that the Sevian lines are concurrent. It's a little bit, it seems strange, yeah? So what you have, so here we don't know that the Sevian lines are concurrent. Of course, two of them will intersect at a point, but there is no guarantee that the third one passes through that point. Let me call it, I don't know, M as before. But I want to tell you that if this is given to me, that between the sizes of these line segments I have this equality established, then the mathematical consequence of this assumption is that these Sevian lines are actually concurrent. Yes. So what I'm saying is that, how should we write that? So for example, if I have this picture, but I don't know that they are, and I don't know that they are concurrent. So let me clean this. Okay. So what I know is this. I know one of these Sevian lines, for example. Of course, I know the second one. Yes. And I know the third one intersect this at a point so that this relation holds. Yes. So I know that Bx time over xc multiplied by cy over ya. And then I know that there is a point on the third one, so that I have. So let me write it in this way. I know that Bx over xc multiplied by cy over YA, okay, multiply by AZ over ZB is equal to 1. This we know. I want to show that if I connect C to Z, it will passes through this point. Yes, is that understandable? So here, in this setup, I have two Sevian lines intersecting the corresponding segments at X and Y, and I know I have a point on the third line. Okay, and I know that Bx time over Xc times Cy over Ya times Az over Zb is equal to 1. My conclusion is, I want to conclude that if I connect C to this point Z with that property, then definitely it will pass through this point. Is that understandable? So the strategy is clear, yes? But I think if you don't have experience, it's very hard to imagine where we should go and how should we prove this theorem. Yes? So I have two Sevian lines, but I do not have the third one. Instead of having the third one, I have a third point. Okay? Z, somewhere. And then I am telling you, assume that somebody measured these lengths and calculated this product and saw that this is exactly equal to 1. What I want to show is to show that if I connect C to Z, it definitely will pass through the intersection of these two Sevian lines. And let me call that point M. I want you to think a little bit about the problem. The problem seems horrible, yes? We probably don't know where to start from, yes? I don't know, what is your idea? How do you want to start solving this problem? What is the strategy? I am asking you about the strategy. I remember when I was at your age, I couldn't solve the Sevas theorem by myself, but I was able to show the other way around myself. The reason is that because I had a lot of experience in the Iranian education system about Euclidean geometry. So you want to prove that the third line passes through M. This way is hard to imagine, yes? But there is a better way to imagine. We actually used this strategy before, yes, by those experiences. What I'm saying is that let me manually connect C to M. This is possible, yes? And then continue it. It will intersect AB at a point. I want to show that point is exactly Z. Remember, this strategy is always, you need to have it back in your head if you want to solve harder geometry problems related to concurrency, yes? So if you want to prove that if I connect these two, it passes through M, it is hard, but let me manually, myself, connect C to M and continue it. If this is true, then the intersection point would be Z. Yes, I need to show that if I connect this one to this one and continue it, then the intersection point will be exactly Z. Yes, is that understand? If I can show that, that's right. And one thing comes to your help is the proof by contradiction. Assume that this is not the case. Okay? So let us momentarily assume that when I connect this to that, I don't know, for example, of course in reality it will pass through this one, but let us assume that no, it will not go and reach to Z, but definitely it will reach to some point, let us call it Z prime. Yes? Is that clear? So I myself connect this one to this one. I want to show that it will go and hit Z. If you say no, then it means that it will hit this point at a different point, Z prime. Is that correct or not? Okay, now Consider these two Sevian lines together with this dotted Sevian line. Are they concurrent or not? These three ones. Yes, the two black solid ones and the red dotted one I drew myself. They are concurrent. Yes, because I did it myself. So I can use the Sevas theorem. So can you just tell me what happens for Sevas theorem? So I would say that AX, of course I have to write all these things if this is an exam. You need to define your strategy the way that I defined you orally. But after that you say that AX, BY, so you after explanation, and then you say then AX, BY and CZ prime are concurrent Sevian lines, yes? Therefore, according to Sevas theorem, okay, tell me, what should I write? According to the Sevas theorem itself, I know that I have three concurrent Sevian lines, so what can I write? The famous formula for Sevian line. So what can I write? I can write Bx over xc, just tell me, I want to test your understanding, okay? Multiplied by cy over ya, multiplied by, no, az prime, yes. Az prime over z prime b is equal to 1. Yes? On the other hand, you are telling me this is also true, because that was the starting point. Yes? So this means that these two numbers, this is 1, this has to be 1, so they have to be equal. Yes? Is that right? So this means that, because this was my assumption, don't get confused. I knew about this. I didn't know if they are concurrent or not. I myself connected this to this M and continued. If you agree with me that this will hit here at Z, we are done. Yes? We are in peace, yes? Otherwise, if you want to fight, it means that it will go and hit this one at a different point, Z prime, but then I will have three concurrent Sevian lines, so I can use the Ceva theorem, yes, and write this. So on the one hand, I have to admit this, on the other hand, I have to admit this. But both of them are equal to 1, so they have to be equal themselves, yes? So then it means that, therefore, bx over xc dot cy over ya dot az over zb is equal to bx over xc dot cy over ya dot az prime over z prime b. Okay, and then I divide both sides by that. I divide both sides by that. Yes? So then what happens? It becomes az over zb is equal to az prime over z prime b. Yes? And now one more step. If you remember, of course you might get the temptation that, okay, z is equal to z prime, but I don't think it's a good idea to do it right now. I will combine it with its denominator. I would write az plus zb. I hope that these kinds of calculations are now easy for you. So is that understandable, that what I'm doing? So I am concluding this from the previous one. Do you remember we could combine the numerator to the corresponding denominator, and still we have the true equality. You remember I told you that if A over B is equal to C over D, I can conclude that A plus B is equal to C plus D. Do you remember we talked about these things? So I'm using that. But the point is that AZ plus ZB, what is AZ plus ZB? Is AB. So I can write AZ over AB, AZ prime, but what is the denominator of the second one? AB. Yes? But now I have two fractions, the denominators are the same and they are equal, so the numerators has to be the same. Yes? So what does it mean? It means that from A to Z is equal to from A to Z prime. So it means that Z and Z prime are the same. Yes? So this implies that yes? So it means that if I connect this point to this one and continue it so that it will intersect AB at some point, this point is the same as Z. So it means that they are actually concurrent. Is that understandable? So you see, it was not that hard at all, but this, if you don't have this strategy, if you do not have the correct mind setup, might be working on this problem as well. But now you have a lot of experience, yes? Is that clear? Okay. Now, I like this theorem because it unifies all those concurrency theorems that we had before. Yes. So we learned that there are three famous Sevian lines in a triangle. What are they? One of them we started first was median, and then was the angle bisector, and the other one was the altitude or height. Of course, perpendicular bisectors are also concurrent, but they are not Sevian lines because they are not passing through the vertex. Okay? But the question is that, can I use the converse of Sevas theorem so that, by the way, be careful, this is the word that I'm using is terminology, converse. You don't use the word inverse or the reverse, even though they are natural. So the mathematical term is the converse theorem. P implies Q. This is called the premise or hypothesis, and this is called conclusion. If you interchange these two, this is not called the reverse or inverse. This is called the converse statement. Okay, so remember this word. So if you interchange the premise and the conclusion, you get a statement which is called the converse of the previous statement, and hopefully you know that even if this is true, there is no guarantee this is true. Yes, be careful about that. So, okay, now let us go back and see what can we do with medians. So now, why do you think medians are concurrent? Do you remember we proved medians are concurrent with a different strategy, and then when we wanted to show that angle bisectors are concurrent, we used completely different strategy, and then I wanted to show that the heights, the altitudes are concurrent. I even do a little bit more strange ones. Do you remember? So the strategies that I used to prove the concurrency of those Sevian lines were quite different from one each other. But now under this one single theorem, all of them can be unified in one single way. Okay? So for example, why medians are concurrent? Let us check. Median goes from here to the middle. So if I call this A, B, C, this will be Bx, and then this will be Cy, and then this would be Cz. Of course, we don't know if they are concurrent or not. But let us calculate Bx for xc multiplied by Cy over Ya multiplied by Az over Zb. Yes, let us calculate this. What happens? Bx and xc are the same for medians. They have the same length if they are medians. So bx over xc is 1. Cy over Ya is also 1. And the other one is also 1. So as simple as that. Because the product is 1, they are concurrent. Yes? So I was able to show that medians are concurrent with a very, very simple way. Yes? I even did, so you know, of course, we learned a lot of things. We learned that the centroid divides a median into the ratio of 2 over 1. So that is also good to know on its own. So this was not a waste of time. But at least this theorem for me is really beautiful because it unifies things, you know. Okay, now this was the simplest one. Let us go to the angle bisector. So why angle bisectors are concurrent? Let us check. You can think about it when I'm erasing the board, okay? So let us go and talk about angle bisectors. Let me draw this angle bisector, divide this into two equal pieces. Of course, I should usually call it D, but let me in this context call it Bx. But I know that this angle and that angle are equal. And I do the same thing here. Okay, let me call it By, and I don't know still that this is passing through this one or not, but let me call this one Z. So this one is equal to that one. This one is equal to this one. Yes? Okay, why they are concurrent? Let us see if the converse of Sevas' theorem will help us or not. So I need to calculate Bx over Xc multiplied by Cy over Ya multiplied by Az over Za, Zb, and hope that I can show that this product is 1. But this is also simple. I don't know, do you know how to do that? If these are angle bisectors. We studied that before, and that's a Mat 2C theorem. You need a theorem, of course. If you have forgotten that theorem, there is no that hope that you can create it right on the spot. I told you that it is very, very important to remember these theorems. So what was the famous theorems for angle bisectors? So let me just remind you, this is important, don't forget about this. If you have a triangle, this is a Mat 2C problem, yes? If you have this angle bisector, I told you that, for example, if this is C, this is B, and if this part is M and this part is N. For angle bisector, we had the famous theorem that M over N is equal to what? C over B. Yes? Is that right or not? We had this theorem. And then we are done. Yes? Why? Because now can you tell me, if this is angle bisector, what is Bx over Xc? What can I write?
AY plus YC.
No.
AB over AC.
AB over AC. Yes? The sizes, yes? This one divided by this one, AB over AC.
Yeah, but I mean AY plus YC is equal to AC.
So why should we write that? No, we don't need to break it. Of course, you are right. But why we should do that? I just write AB over AC. Yes? Okay, let me ask you one more time. This is also angle bisector. So can you tell me what should I write? CY over YA is equal to what? You need to see the problem from this angle. What happens? If I draw this angle bisector, if I clean this, I draw this angle bisector. If this is M, this is N, then what can I write for M over N? M over N is BC over AB. Yes, that's the same theorem, seeing it from this angle. So CY over YA is what? Is BC over AB. Yes, agree? And then what can I write finally? AZ over ZB, because that is also angle bisector. What is this one equal to? AZ over ZB. What can I write in front? Tell me. What is that? I don't know, why do you find it hard to say? What is that?
AC over...
Yes, AZ is this one. It's below AC. Yes, over?
BC.
Over BC. Yes? Now I multiply BX by XC, CY by YA, and AZ by ZB. Then what happens? Instead of this one, I can put AB over AC. Instead of this one, I can put BC over AB. And instead of this one, I can put AC over BC. But this BC and that BC are gone, AB and B, and AC and AC. So again, this is equal to 1. Yes, so I calculated that one, and it becomes equal to 1, so they are also concurrent. Okay, now I pause the recording. I want you to do the same strategy to prove that the heights are also concurrent. Yes? I will give you 10 minutes to think, and then I will come back to you. So is the question clear? So use the converse of Sevas theorem to show that the heights are also concurrent by any means that you know. Even if you want, you can use trigonometry or whatever. So might be, I haven't thought about that, but I'm sure that this is possible using Sevas, the converse of Sevas theorem. So let me try, for example, try to draw one picture. You don't need to draw all the heights for the time being. So we have A, B, C, and let me draw this one and call it AX. So my point is somehow to write BX over XC. Yes? Let us see if I can find something nice for this one. For median, it was trivial because BX over XC was 1. For the bisector, at least we have an auxiliary theorem. We use that part, yes. If it was not there, this bisector was also hard. But for heights, we do not have actually something specific in our hands. So we need to invent it ourselves. So what do you think? Well, how have you thought about this? Nothing?
I used the Pythagorean theorem.
No, that would be hard. Because
hard, yes.
it becomes, it makes squares and everything involved. So that you need to give up. The other thing. Okay, so let us use this trick. Let me call this one C, let me call this one B. I told you use trigonometry. I was thinking that might be it will help. And it will help actually, I think. Because BX, I will write something, you just tell me do you confirm it or not. So if I write tangent of B, what happens for tangent of B? It becomes this height, the opposite side divided by adjacent side. Yes or no? Okay, and then if I write tangent of C, it becomes the opposite side, which is AX again, divided by CX. Yes or no? Okay, now my goal is to have BX over CX. So I hope that you understand immediately. What can I write for BX? I interchange these two. Yes, I hope that you are now very quick in understanding these things. Okay, so I interchange them, so it becomes BX is equal to AX over tangent B. Do you have any problems understanding this? Instead of BX, I wrote this. Is that understandable? Because I can interchange these two, I told you before. Okay, and instead of xc or cx, what can I write? Cx and xc are the same. I can interchange them. So it becomes ax over what? Tangent of c. So this ax and ax are gone. And then tangent c goes to the numerator. Yes or no? So we got that bx over xc is equal to tangent of c over tangent of b. And that is what you really need, nothing more. Because, do you agree that I can just repeat this argument once more from the other side? Yes? So, for example, let me just I want to test your understanding. So this is actually a kind of symmetrical argument. So here, if I go here, this height, let me call it by. I need to find cy over ya. Either you repeat the whole process once more, but I think you can guess what will happen, yes? Can you tell me what will happen if I follow the same line of arguments, but this time on this side? Because you see, b was here, tangent of b was here, c was here, tangent of c was there. So what will happen in the denominator? What will appear? Tangent of c. In the numerator? Tangent again. If you don't believe, you have to repeat the process again. Yes? And then let go back to the other one, which we don't know yet. So what will happen for cz over z? No, sorry. az over zb. Okay, so if I clean these heights and then concentrate on the third one, then what do you think will, if I follow the same line of argument here, what do I get?
Tangent b over tangent a.
Yes. You see, it was not hard. You need to ask yourself why I could not understand that. But then is it done? Yes? Because if I multiply this by that, I have to multiply this by that. But then what happens? This one and this one are cancelled. This one and that one are cancelled. These two are cancelled. Again, that's equal to 1. Yes? So this, you need to take a lesson why you couldn't understand this, because it was not that hard. So you need to try to teach yourself. This is something that I cannot teach you. I can just draw your attention to it. But then you need to teach yourself, okay? The next time I will solve the problem. Yes, that's the only thing that we can do. Okay, so here, this is a nice theorem. You see that one theorem helped me to prove the concurrency of all those, yes. And then I will try to find or design some nice problems using Sevas theorem, and I will bring them up in the set of problems. But designing these questions or finding them appropriately, because when I want to, even if I want to find them, I need to know which theorems you are supposed to use them. And if you haven't studied them, that's pointless, unless I give you the hints in the question itself. So the designing of these questions are not that easy, but I will try to do my best to make it ready by Sunday. Okay, is that understandable? Okay, so now we learned a lot of things about Euclidean geometry. I don't know, by the way, did you like it or not that much? Do you like Euclidean geometry? I think this is an ultimate tool in our hand for thinking. I don't think you can find something harder than geometry to think about. There are problems that you can even imagine. I don't know how these people in mathematical contests. Of course, I can imagine they have been training themselves for really 8 hours a day for 1 year probably. Then they can crack those problems. Then you cannot imagine how creative you have to be to understand to do these things, for example. Yeah, it is very, very hard. Number theory and is also very hard that we're actually dealing with in Math 5. Okay, I will stop here and I will not continue this lesson here. Next time we'll go back to vectors, okay? And then whenever necessary, I will come back to Euclidean geometry. And I hope that we can also cover some kind of mechanics and physics, so that you can see when the mathematics you are using, how they are really useful. Especially trigonometry, after this chapter is finished, might be we can deviate a little bit. Have you studied projectile motion in physics? Yes, then That's a very good mixture. So we can have some kind of those ideas. After we learn a little bit about vectors, then I can come back and teach you a little bit about those things in combination with mathematics. Okay. So I will stop here, and then if you have anything to do, you can work on that. Thank you.